This represents 100 samples, each described by 50 features. Think of it as a spreadsheet with 100 rows, samples, and 50 columns, features. Each cell contains a measurement for that sample and feature. This is a single column with 100 rows, representing the desired outcome or response for each of the 100 samples in X. For example, if you're predicting house prices, each entry might be the price of a house. I calculate this by multiplying the transpose of X, T, with X itself. It's like summarizing all the relationships between the features in X, and using this summary helps speed up the feature selection process significantly. It's optional, but using it is a shortcut to faster results. This is a setting that tells the algorithm to select at most 5 features. The algorithm might choose fewer if a smaller number of features can accurately represent the target vector Y. These are the main ingredients of the orthogonal matching pursuit algorithm: the data, X, and what we're trying to predict, Y. The algorithm outputs a list of 5 numbers. Each number corresponds to the column index, or feature number, of a selected feature in the original design matrix, X. For example, if the output is 1, 5, 10, 20, 40, it means that features 1, 5, 10, 20, and 40 are the most important features for predicting Y. This is the feature selection method I'm using. OMP is a smart way to pick the most relevant features from your data. Orthogonal_MP_gram is a specific scikit-learn function to implement it efficiently. I'm using scikit-learn's orthogonal matching pursuit, OMP, algorithm, specifically the orthogonalmpgram function. It's a method for selecting the most important features from a dataset. OMP is a greedy algorithm. It selects features one by one based on how well they reduce the error in predicting the target variable. The orthogonalmpgram version is optimized to work with a pre-computed gram matrix, which you'll see shortly. I have a design matrix, X, which is a 100 by 50 matrix. This means I have 100 samples, data points, each described by 50 features. My target vector, Y, is 100 by 1, which means I have one target value for each of my 100 samples. My goal is to use OMP to figure out which 5 of these 50 features are the most useful for predicting the target. The orthogonalmpgram function will give me back a list of 5 numbers. These numbers aren't the values of the features, but rather their indices asterisk, the positions of the selected features in the original feature list. For example, if the output is 1, 5, 10, 20, 45, it means features at positions 1, 5, 10, 20, and 45 are the most important. Here's the cool part. The gram matrix is simply the matrix product of the transpose of X, XT, and X. Calculating it beforehand lets orthogonalmpgram run much faster because it avoids redundant calculations. That's a huge efficiency boost. This is confirming what I already told you about the output. A vector, a list of 5 numbers which directly tell me the positions of the most important features in my original dataset's 50 features. Important note: orthogonalmpgram does not automatically scale the features. You might need to scale your data before using it. This is because features with larger values can disproportionately influence the algorithm. If I set, it means I want to find up to 5 features. The algorithm could potentially find that it can do a good enough job of predicting the target with fewer than 5 features and will stop earlier. This question focuses on how to pick the 5 most important characteristics from a dataset using a specific machine learning technique called orthogonal matching pursuit, OMP. I'm given a dataset with 100 samples and 50 features, and I need to determine which 5 features best predict the outcome. This is my dataset. It's a table with 100 rows, samples, and 50 columns, features. Each cell represents a sample's value for a specific feature. After using the algorithm, I get a list of 5 numbers. Each number represents the column, feature, index chosen as the most important ones. So, I will know exactly which 5 features the algorithm selected. Pretty cool, huh? The gram matrix is a special type of matrix calculated by multiplying the transpose of my feature matrix, X, by itself, X. The algorithm can use this pre-calculated gram matrix to run faster. It's like pre-doing some of the heavy lifting to make the rest of the work quicker. This tells the algorithm to select at most 5 features. The algorithm may select fewer than 5 if it finds a good enough solution. It won't always pick exactly 5. Nope. I must scale my features before using OMP. The algorithm doesn't automatically do it. Imagine features with very different scales, some tiny, some huge. The algorithm might unfairly favor the large ones. Scaling ensures all features have a similar range of values. Incorrect. The parameter sets a * maximum limit to the number of selected features. The algorithm is smart enough to select fewer if it can achieve a good prediction without needing all 5. It's a greedy algorithm, but not a stubborn one. This is the specific machine learning algorithm I'm using to select the most relevant features. OMP, orthogonal matching pursuit, is a technique for finding the best features by iteratively adding features that improve the model most. The function _orthogonal_mp_gram_ is an optimized version of OMP that leverages pre-computed gram matrix for faster computation. I'll explain this step by step. First, we use Sklearn's OMP algorithm, specifically the orthogonalmpgram function. This function is a smart way to find the most important features in your data. Think of it as a detective finding the most crucial clues in a case. It uses a clever mathematical trick to do this efficiently, which is explained in the next steps. Our data consists of a design matrix X, 100 samples, each with 50 features, and a target vector Y, 100 samples with one target value each. Imagine X as a spreadsheet of measurements, 100 rows representing different people, each with 50 columns indicating different characteristics like weight, height, blood pressure, etc. Y is the outcome we want to predict, such as whether a person has a particular medical condition. The algorithm tries to figure out which characteristics in X are most relevant to predict Y. I feed orthogonalmpgram our design matrix X and target vector Y as input. The algorithm uses these to find the important features. Optionally, I can pre-compute the gram matrix. This is X transpose multiplied by X, X. This is a clever optimization. Calculating this ahead of time makes the main algorithm faster because it avoids redundant calculations. The output is a list of the indices, positions, of the 5 most important features in the design matrix X. For example, if the output is 1, 5, 10, 20, 45, it means that features at positions 1, 5, 10, 20, and 45 of the original data are selected as the most relevant to predict Y. These are the clues that the detective found. I'm using Sklearn's orthogonal matching pursuit, OMP, algorithm, specifically the _orthogonal_mp_gram_ function. It's a method for selecting the most important features from a dataset. Think of it like choosing the most influential players from a sports team to explain the team's overall performance. We have a design matrix X, which is a 100 by 50 matrix. Each row represents a sample, and each column represents a feature. We also have a target vector Y, which is a 100 by 1 vector representing the outcome or response I'm trying to predict. Think of it like this. X shows the attributes of 100 houses, size, location, etc., and Y shows their prices. The _orthogonal_mp_gram_ function can take 2 types of input: the original design matrix X, or a pre-computed gram matrix, X. T and X. The gram matrix is simply the matrix product of X transpose and X. Using the pre-computed gram matrix can speed things up significantly, especially for large datasets. It's like having a pre-made ingredient instead of preparing it from scratch. This is the core function I'm using to perform the feature selection. It uses the orthogonal matching pursuit algorithm. It's a smart algorithm that iteratively selects features that best explain the target variable. The function gives me back the indices, locations, of the 5 most important features. It doesn't give me the feature values *, just their positions in the original data. It's like getting a list of the best players' jersey numbers, not their stats. This statement is true. I can give the algorithm the pre-computed gram matrix to make it run faster. Absolutely correct. The result will be a list of 5 numbers telling me where the best features are located within my dataset. This is false. The _orthogonal_mp_gram function does not automatically scale the features. I need to do that myself beforehand to prevent features with larger values from dominating the selection process. Incorrect. _n_non_zero_cofs equals 5 sets a asterisk limit of 5 features. The algorithm might find a good enough explanation with fewer than 5 features and stop early. It's a smart algorithm. I'm using Sklearn's orthogonal matching pursuit (OMP) algorithm, specifically the orthogonalmpgram function. OMP is a feature selection method. It helps you pick the most important features from your data. The orthogonalmpgram function is a particular implementation of OMP that's optimized for speed. I have a dataset. X is my design matrix. It's a 100 rows by 50 columns table representing 100 samples with 50 features each. Y is my target vector. A column with 100 rows representing the outcome I want to predict. I'm going to test your understanding of the orthogonalmpgram function and OMP. I'll give you some statements, and you need to tell me which ones are correct. This statement says that orthogonalmpgram works faster if you give it the gram matrix, XX, the matrix product of X transpose and X, beforehand. I'll explain the gram matrix concept in the solution section. The function's result will be a list of 5 numbers. Each number is an index pointing to one of the 50 features that were chosen as most relevant by the algorithm. This statement suggests that the algorithm automatically adjusts the scale of features. I'll tell you if this is true or false. This says that no matter what, the algorithm will always return exactly 5 features. It doesn't consider whether fewer would be sufficient. I'll explain this statement's validity. We're working with a dataset. X is our design matrix, a 100 by 50 table representing 100 samples with 50 features each. Y is our target vector, a 100 by 1 column representing the outcome we want to predict for each of the 100 samples. Think of it like this. We have 100 patients, samples, 50 measurements on each, features, and a single outcome for each target variable, like whether they have a disease or not. I'm using the design matrix X, 100 samples by 50 features, and the target vector Y, 100 samples, as input for my feature selection process. These are the data I need to find the most relevant features. To speed things up, I can pre-compute a gram matrix. It's essentially the matrix product of X transposed and X. X at X. This matrix holds the dot products of all feature pairs, providing handy information for the OMP algorithm. I'm using the orthogonal matching pursuit, OMP, algorithm. This is a greedy algorithm that iteratively selects features that best explain the target vector Y. It's like building a model step by step, choosing the most impactful features one at a time. The algorithm's output will be a list of 5 numbers, the indices, positions, of the 5 features determined to be the most relevant. I won't get the feature values themselves, just their positions in the initial feature set. I'm applying the OMP algorithm. The gram matrix input gives the algorithm a head start. Instead of recalculating relationships between every feature pair multiple times, it can use the pre-computed relationships from the gram matrix. This significantly improves computational efficiency.